Good morning, ladies and gentlemen. Today we're going to be continuing with magnets, and we're going to be learning the relationship between magnets and electricity. So it starts us off with a prompt about electromagnets. It wants to know, why is the word electro used to describe such magnets? Okay, is electricity involved in their operation, or do they create their own? And what type of current would these magnets require? Okay, first of all, how did we learn that magnetic fields and electricity are related? How did we learn that? How did we figure that out? Well, somebody at some point accidentally brought a compass near a wire with flowing power. Okay. When you bring a compass near a wire that has electricity flowing through it, it's moving, the compass starts to act up. The only reason the compass would act up is if there is a magnetic field being produced by the current. So this is how we learn that moving electricity or moving electrons, that flow produces a field. That is the only logical explanation. That's the only thing that can happen. So electricity, the flow of it, equals magnetism. Okay, just moving electrons produces a field. Okay, so that's what an electromagnet is. An electromagnet is a magnet that uses the flow of electricity to produce a magnetic field. So to answer the question, yes, electricity is involved. They do not create their own electricity. They use electricity to produce a magnetic field. Okay. Electromagnets have very large potential and they can produce a lot of magnetic force. I'll give you an example, the junkyard magnet. What's cool about electromagnets is that you have the ability to turn them on and off. Okay. You can control when they're magnetized and when they're not. So you flip the switch, you turn on the current, and the electromagnet turns on. And it's very powerful. It can pull up all these brake pads. You drag it to where you want to drag it to, and then you can simply flip a switch and turn it back off. That is the advantage of an electromagnet. You cannot turn on and off a fridge magnet, for example. You can't decide suddenly, I don't want you to be a magnet anymore. You can't do that. But with electromagnets, you can. Okay? So, in which direction is the magnetic field going to go when you flip the switch? It depends. You can figure that out with the right hand rule. So, what the right hand rule tells you is what to do with your hands in order to figure out the direction of the field. Okay. So, step one, it says point your thumb in the direction of the current. So, if we know that electricity is flowing from the bottom of this wire upwards, we know the direction, we know the current. Okay. I is the symbol for current. So, the current is going from the bottom to the top. So, point your thumb in that direction. Cool. The direction that your fingers curl in are going to be the directions of the magnetic field. The letter B is the symbol for magnetic field. Okay, so notice how the magnetic field goes around in a circular loop around the wire. Okay, it goes around in a circular loop around the wire. That's why we use the curl of the fingers. So, and the direction your fingers are pointing in. So note the direction that these fingers are pointing in. That will tell you the direction of the field. So the field is looping around, and it's looping around. This would technically be counterclockwise. Okay, it's looping around in this direction counterclockwise. So point your thumb in the direction, and that will tell you the direction. Okay. Things get weird when you start adding loops. So just to prove to you that the magnetic field can change based off of this loop, think about this easy part in the beginning. So in the beginning, it's flowing this way, and at the end, when it comes back around, it's flowing this way. That is going to affect the fields as the curl is going to change. So when you come around going upwards from bottom up, the curl is going to be this way. Okay, it's going to be curling up. It's hard. to show, since I don't have 3 dimensions and I'm not in front of you to kind of demonstrate, but it would be curling this way. It would be going clockwise. But if we're coming around this way, it's going to now be curling down counterclockwise. So as the current comes in, the magnetic field flows clockwise, and as the current comes out, it switches to counterclockwise. So as this current flows around, the magnetic field, the direction of it is going to change as it passes through. Okay. I'm not going to bother trying to draw everything because it would probably confuse you more than help you. But that's the idea. Hopefully what you see here in the beginning can prove that to you. In the beginning, it's flowing this way, in this direction, from bottom right to top left. That gives you a clockwise curl. You flip that, you get a counterclockwise curl. So as it goes around the loop, it changes. Why is that important? It's important because it proves or demonstrates that a looped wire produces the same kind of magnetic field that a bar magnet does. That's why this piece was relevant. That's what they were trying to prove to us or show us. Okay. And look here. On the right side, what do you notice? The arrows are flowing in a clockwise direction, and on the left side, it's flowing in a counterclockwise direction. Look at the direction of the arrows. That's what I was trying to show you. And then they compare it to a bar magnet. Bar magnet, it's producing the same lines. Look, the exact same lines. So this is how we began the process of developing electromagnets. So this is one single loop. This is multiple loops, okay? It's looped around over and over and over and over again. And the more loops you put on it, the stronger the magnet it can become, okay? So we call this a solenoid. A solenoid is a coil of wire. So instead of it being a single loop, it produces a bunch of loops, okay? The more loops you have, the stronger the field, okay? More loops strengthen the field, okay? And then what you can do is once you get this wire wrapped around, if you put a ferromagnetic material, yesterday we talked about ferromagnetic materials. A ferromagnetic material is anything that can be magnetized. If you put a ferromagnetic material in the middle of a solenoid, it basically it's a magnet on steroids at that point, is what that does. The ferromagnetic material is the steroid for the magnet, okay? And then at that point, that's when it technically becomes an electromagnet. So an electromagnet is a solenoid. It's a solenoid with a ferromagnetic material in the middle. And normally we use an iron rod, okay? So solenoid plus iron rod equals electromagnet, okay? So that is how we produce electromagnets, and that is what they are. They are coils of wire with a ferromagnetic material in the middle, okay? And it does produce the same magnetic fields as any other magnet would, except we can make it a lot stronger, okay? So that's the relationship between electricity and magnetism, okay? The flow of electricity can produce magnetic fields, okay? And eventually, when we start talking about generators, we'll see that we can use magnetism to also produce electricity. Electromagnets use and consume electricity, but generators use magnetism to actually produce electricity. Okay, so it can go both ways. And well, the generator one is a future topic, but that's what I wanted to discuss for today. So now we can answer these questions. Why is the prefix electro being used in these magnets, or just used to describe them? It's because the electricity is being used to produce a magnetic field. Okay, so it's being consumed, not created. Okay, and in terms of what type of current, that's something we'll talk about in the future. That's a future question. All right. Well, thank you guys for your time. I wish you all the best. There is a study guide that I'm going to have you guys work on today, section 2 study guide. It's, I believe it's 3 or 4 questions, if I remember correctly. So it shouldn't be too much of a hassle. But again, if you have any questions, feel free to reach out. Appreciate you guys. Hope you guys are doing well. Take care and enjoy the rest of your day.